Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will discuss the human physiology. Now in today's lecture we will discuss the thermodynamics of human body, heat balance of body, effect of heat on work performance and human body temperature regulation. Now energy we draw to do the work is through metabolic reactions. Metabolic reaction. Out of these reactions, the energy is evolved, and approximately 20% of this energy is used for doing the mechanical work or external work. So, if we consider our body as an engine, the efficiency of our body is 20%. 20%. Now, where does this 80% heat go? It cannot be stored in a body, because if the heat is stored in a body, the temperature of the body will start rising. So, this heat has to be dissipated to the surroundings. Now, here the dissipation of heat to the surroundings also depends upon the surrounding conditions. Now, in India, the climate varies from north to south and east to west and north to south. We have, if you go to the western side of India, especially in Rajasthan, the climate is maybe 47 degrees centigrade temperature and relative humidity, this is DBT, dry bulb temperature, and relative humidity may be of the order of 10%, 10 to 20%. This is extremely dry weather. If proper hydration of body is not maintained, this can be fatal also. Now, another extreme climate we are having, like a coastal area, the dry bulb temperature is typical of coastal climate, maybe 35 degrees centigrade. Relative humidity may shoot up to 70 or 80%. Now, heat dissipation of human body will differ in this condition and in this condition. The mode of heat dissipation and heat dissipation from body will differ, and body temperature has to be maintained constant. The body temperature, our body temperature is 36.9 earlier. It was 98.4 Fahrenheit. Nowadays, it has been corrected to 37 degrees centigrade body temperature and 98.6 Fahrenheit. Our body is a homoexothermic machine, and the body temperature has to be maintained constant under all the circumstances, under all the environmental conditions. There are two states of body, that is hypothermia, and another is hyperthermia. In hypothermia, when the temperature is less than 35 degrees centigrade, and these are very serious situations when temperature is less than 35 degrees centigrade or temperature is greater than 40 degrees centigrade. Both are very serious conditions. When temperature is, let us say, 40.9 degrees centigrade, it is equivalent to 104.5 degree Fahrenheit. Right? So, when the patient enters this body temperature, it is assumed that he has entered into danger zone, because the moment the temperature becomes 41 degrees centigrade, and patient is likely to be unconscious. On the other hand, if the body temperature is 20 degrees centigrade, then there are chances of cardiac arrest. So, a constant 37 degrees centigrade temperature has to be maintained inside the body. So, a proper heat balance of heat emitted from human body is required, because metabolic rate is a continuous rate of heat evolution from the body. Now, if we write the heat balance equation, that is heat in metabolism minus work done, that is energy consumed by doing some work, is equal to, now one mode of heat transfer from the body can be evaporative cooling, so that is QE. Another is conduction from the body, and conduction of the body can be in both direction. If suppose outside temperature is high, heat will be conducted to the body, and outside temperature is low, heat will be dissipated from the body. Same is with the radiation heat transfer. Radiation heat transfer will also take place. Maybe the temperature difference, body temperature difference and outside temperature. So, body temperature and outside temperature difference may be of 5 degrees centigrade, but some amount of radiation heat transfer shall also take place, plus QS, heat stored in the body. So, this has to be 0. In ideal condition, if the body starts storing heat, then the temperature of the body will shoot. Now, there is a generalized correlation, because when we talk about the heat transfer, heat flux is more relevant. For engineering practices, heat flux appears to be more relevant when we want to do the engineering calculation. So, in that case, we must have the body surface area of an individual, right. It is very difficult to predict, but many samples were taken, and a generalized correlation for body surface area, that is AD, is equal to 0.202 meter, 0.425, and this is height in meters, 0.725. Now, using this formula, you can also find the body surface area of, for an average European, it is found to be 1.8 meter square male, and for female it is 1.6 meter square. So, for yourself also, suppose I take a case of, let us say, mass is 65 kg or 70 kg, height is 1.7 meter. Let us see what is the body surface area of an individual, that is 70 raised to power 0.425. 70 raised to power 0.5 will give us m raised to power 0.425 will give 6.083, and L is 1.7. So, L raised to power 0.725 will give, this is 1.7 raised to power 0.725 will give, 1.7 raised to power 0.7, it will give 1.469, and if we multiply this and this, then we will get body surface area, and that is going to be equal to 0.202 multiplied by 6.089 multiplied by 1.469, approximately 1.8 meter square. So this is how you can find your body surface area also, and this is known as Du Bois equation. This is known as Du Bois equation. Similarly, metabolic rate also you can calculate. Metabolic rate for yourself you can also calculate by using the equation metabolic rate M is equal to 21 0.23 RQ plus 0.77 QO2 divided by A. Now you have the area, right? Now you have body area. Now you have two unknowns, that is RQ and QO2. Now RQ is the respiration quotient, molar ratio of CO2 and oxygen inhaled and carbon dioxide exhaled. So this is the molar ratio of carbon dioxide exhaled and oxygen inhaled. Normally inhaled and exhaled gases are measured in volumes, liters or milliliters. So if you have this measurement in liters, using PV is equal to MRT, you can always find the mass of oxygen inhaled, and once you know the mass, you can always find, and you can find from here itself M universal gas constant T divided by molecular weight of oxygen, right. So moles of oxygen you can find from this formula itself if you have the volume of the oxygen consumed, right. Similarly, you can find the moles of carbon dioxide in exhaled air, and ratio of these two will give you the respiratory quotient and QO2 is volume rate of oxygen consumption. If you take volumetric rate of oxygen consumption at normal temperature and pressure, it means 0 degree centigrade temperature and pressure is 101.325 kilopascal, right. Now having the value of respiration quotient and oxygen consumption, metabolic rate can be found out. So in a human body, now we can calculate the area of human body, we can find the metabolic rate of the human body, and metabolic rate is important. So normally for a human body it is assumed that in a sedentary activity, suppose somebody is sitting on the chair and doing nothing, in that case the metabolic heat evolved from the body is 100 watts. Now if I divide this by surface area, I will get the heat flux, and that heat flux is approximately 58.1 or approximately 58 watt per meter square, and this is known as 1 MET. Metabolic rate is not expressed in terms of watts, it is expressed in terms of MET, and 1 MET is approximately 58 watts per meter square. Now we can have different metabolic rates for different, somebody is doing wrestling, for wrestler it goes up to 7 MET. So the rate of heat coming from the body is often expressed in terms of MET. When effective temperature of work output is, effective temperature I have already explained you earlier, is increased to 26 degree centigrade, it is the estimate that the work output will reduce by 10%, and when it exceeds 34 degree centigrade, work output remains only 40%. So temperature is a major governing factor in work. That is why you will find that many of the factories or many of the workplaces where production is important, rate of production affects the performance of the factory, the indoor environment is maintained in a comfortable state. So air conditioning, in fact, in those cases, air conditioning becomes a profitable investment, because the productivity of the worker increases, substantially increases in air conditioned environment. You can see effective temperature is 26, it is reduced by 10%. For effective temperature 34 degrees centigrade, it is reduced to 40%. Now, if the temperature keeps on increasing, if temperature keeps on increasing, the body temperature above 40.5 degrees centigrade, the body will experience heat stroke. And heat stroke, before heat stroke, there are certain other stages also. I will take them one by one. First is heat exhaustion. So, heat exhaustion around 40 degrees centigrade, it is due to two reasons: shortage of water and second is salt deficiency. Salt deficiency. Now, in this heat exhaustion, the person feels tired, giddy, nauseated, and sometimes chilly also. But these three symptoms are there when there is a heat exhaustion, and the best thing is to give water to the patient. If proper supply of water to the patient is made, this problem can be avoided. In this case, the patient also feels shallow breathing and color of the skin also changes to pale. So, they are symptoms, and immediately the symptomatic relief will come the moment the water is supplied and water with the salt is supplied. So is the case with the salt deficiency. If proper salt is provided, supplied to the patient, he will recover from this. Now, another case is a second one, that is heat syncope. Now, in heat syncope, in this case, what happens due to high temperature above 40 degrees centigrade, the arteries and the veins, they get dilated. When the veins and arteries get dilated, the blood is pooled in the lower half of the body and proper blood circulation is not there for the brain, and patient becomes immediately unconscious. So, you must have heard or you must have seen people standing in the hot environment, hot outdoor environment, all of a sudden they collapse, right? The reason being there is a shortage of blood supply to the brain, and a pool of blood is formed in the bottom half of the body near the legs due to dilation of veins. So, immediately this patient should be laid down in a shadow area, and his head should be kept below the other parts of the body. So, there will be proper supply of blood to the brain, and immediately within 5 and 10 minutes the patient will recover. Now, the third is heat stroke, which I was talking about earlier. Now, in heat stroke there is no sweating, and it can be fatal also. In heat stroke there is no sweating. In heat stroke there is a sharp body temperature rise. No sweating means the cooling mechanism of the body fails, right? And in this case, the patient should be immediately put into the water, or water should be poured over the patient, and immediately he or she should be taken to the hospitals. So, these are the effects on the body of high surrounding temperatures. Now, body has got its own temperature controlling mechanism. These are the extreme cases. Otherwise, body has its own temperature control mechanism. And temperature regulatory center TRC, temperature regulatory center in the body is at 36.8 degrees centigrade. It is in the brain, temperature regulatory center, and at this temperature it controls the body temperature. It itself remains at this temperature. If somebody is walking, this temperature may rise to 37.4 degrees centigrade, and somebody is jogging, this temperature becomes 37.9 degrees centigrade. Right? This temperature regulatory center is known as hypothalamus. It is placed in the brain. Hypothalamus controls the body temperature. Now, the blood in the body has many functions. The function of the blood in the body is not only to circulate oxygen to different parts of the body, but blood also helps in cooling the body in a significant manner. Suppose there is a rise in outside temperature. When there is a rise in outside temperature, the blood flow near the skin will increase. This is known as vasodilation. In vasodilation, in this process, the blood circulation to the skin increases. When the blood supply to the skin increases, the more easily the heat can be dissipated to the surroundings, right? So, in vasodilation process, the dilation of veins takes place, and for normally the flow rate of blood is ml per second per meter square. It is this is the normal blood flow rate in a vessel, and it can go up to 15 times 25 ml per second per meter square. So, blood flow can increase 15 times near the skin in order to dissipate heat to the surroundings. Now, why I am writing per second per meter square? Reason being, in many of the fluid mechanics analysis or two-phase flow analysis, especially two-phase flow analysis, the mass flow rate or mass flux is expressed in kg per second per meter square. And this becomes important here itself, because in engineering practice the passage has a rigid wall. I mean, if we are analyzing flow in a pipe, the pipe has a rigid wall, right? So, cross section area of the pipe is constant, and we can do fluid mechanics analysis on this pipe. But when we are dealing with the arteries and veins, they are pipes of flexible wall. The moment blood pressure rises, the cross section area of the wall also rises, cross section area also increases. With the pressure they expand. So, in order to express the mass flow rate, it is always expressed in terms of per unit area. So, here also you can see starting from 1.7 to 225 ml per second per meter square, blood flow can be increased to this level. Now, another extreme is when the temperature is low. Vasoconstriction takes place, or cross section area of the blood of the veins which are taking blood through the veins through which the blood is passed is reduced. So, due to this contraction, vasoconstriction in winters, by controlling this blood flow rate, you will get an effect equivalent to the one sweater. Suppose you are in a normal atmosphere and all of a sudden there is a drop in temperature, outside temperature reduces, then immediately vasoconstriction takes place, blood flow to the surface of the skin or just below the skin will reduce, and you will get insulation equivalent to that of one sweater. After that, if more energy is required, then muscles of the body, they start increasing tension. So, they become tense. When the muscle in the body, they become tense, they liberate energy. and that energy, to your surprise, is approximately 4.5 met. Up to 4.5 met energy can be liberated by just pushing or just through the tension of the muscles in the body. So this is how internal heat of the body is liberated just to maintain the body temperature 37 degrees centigrade. So this is inbuilt mechanism in the body which helps in maintaining the body temperature. Another mechanism is sweating. Evaporation from the surface, evaporation of water from your skin, that causes cooling effect. But in some of the cases, for example, this coastal climate, outside air is humid, outside air is already at 80% relative humidity. In that case, the wetting of skin takes place, wetting of skin. Wetting of skin, and you start feeling comfortable when 25%, more than 25% of skin is wet, right? Then normally what happens, people take bath, because this is also accompanied with salsa. It is hygroscopic. It helps in retaining sweat on the surface of the skin. Now one starts feeling uncomfortable, because due to one reason being the friction between the cloth and the body skin increases. That makes you uncomfortable, and when you feel uncomfortable, get a chance, you take a bath. When you take a bath, the body cools down and the salt on the skin is also removed, and you get immediately hypotonic. Sweat film on the surface. So you must have realized that even after taking bath, you start sweating, but you don't feel that uncomfortable as you were feeling earlier. The reason being, your the sweat has become hypotonic, means the salt is diluted. The salt is diluted. The salt is diluted, and that gives you the relative comfort feeling. Now, activities I will take one by one. For example, you are sleeping. When you are sleeping, the activity is 0.7 met, here met. Just to have an idea, I mean, as an engineer, you should have numerical values of that gives you the sound idea. Suppose you are sitting is 1, sitting. And when you are walking, it is 2 met, and it can go up to 3.8 met, depending upon the speed of the walk. If you are walking, it is a brisk walk, it can go up to 3.8 or approximately 4 met. So 4 times energy will be released even if you are walking, fast walking. Okay. If you are typing and writing, it is approximately 1.1 type writing. 1.1 met. Just walking about in the office, just moving around, 1.7 met. When you are driving a car, it can go up to 2. Now car driving can go up to 2 met if you are exerted, right? Now heavy vehicle driving can go up to 3.2 met. So truck driving is more energy consuming, and energy consumption is approximately 2 to 3 times that of driving a car. Even dancing, social dancing maybe 4.4 met. So these are number, or wrestling, yes, wrestling is 7 to 8.7 met. So wrestling is most energy consuming activity. It can go up to 8-7 met in case of wrestling. Basketball also, basketball is 5 to 7.6, tennis. So for different activities, Singles tennis can go up to 3.6 to 4 met. So for different activities there are energy levels, but say wrestling it is very high. But the issue is to what level you can go for up to. So individual's capacity for short duration it can go up to 12 met. 12 met. At the age of 60, that is also related with the age of 20 years, and if somebody is of age of 70 years, it can go up to 7 met only. This is the energy dissipation from the body of an individual, and this also helps us in designing the system. Suppose I want to do air conditioning for the wrestlers, so definitely I must know how much energy is liberated by the wrestlers. So these are the different energy levels liberated by the through different activities. I think that is all for today. In the next lecture, we will take up thermal comfort. Thank you very much.